Okay, thank you very much. So it's great to finally attend the StanCon. I've been a user of Stan for the last around 10 years throughout my PhD and postdoc, and Stan even led me to my current role at Ledger Investing because it was on the Stan Discourse forums that I saw the job advert about 3.5 years ago. So I feel I've got a lot to thank Stan for. So Ledger Investing is a US-based insurance technology startup company. And we're building an online marketplace to connect insurance companies with investors. And part of our work is to model the performance of insurance companies to help inform those investment decisions. And nearly all of our modeling work is based in Stan currently. So this talk is on a very specific area of insurance modeling known as loss development modeling. So the goal of loss development modeling is to predict the total amount of money lost from all claims being reported to an insurance company. And if we imagine that all of us in this room have some car insurance policy with some insurance company, this insurance company has been around for the last 10 years, and then now in 2024, we're tasked with working out how much money is going to be lost from all those claims being reported, which together with the premiums tell us something about the profitability or solvency of the insurance company. So it's common to tabulate and aggregate the data like this. Each cell here is a monetary value of loss that the insurance company will pay out for claims. Along the rows are what we call the accident periods, which is the period of time which an accident occurred. So if you had a car accident in 2014, your claim would go in the top row. If you had a car accident last year, your claim would go in the bottom row. And then the columns tell us the development periods or development lags. And these are simply tracking the cumulative losses through time within each accident period. And because there can be significant delays in the amount of time it takes for people to report accidents to insurance companies, and in the insurance company figuring out how much they're liable for particular claims due to claim litigation processes, we don't know what's called the ultimate losses on this slide, which are on the right-hand side in the hatch boxes, which are the total amount of money the company will be liable for within each accident period. And so now in 2024, we can look back at 2014, and we have 10 development periods to tell us something about the ultimate loss for that accident period. But for last year, we only have one. And so this is a challenging prediction task, because we're usually estimating ultimate losses for accident periods with sometimes very small amounts of data on an aggregate basis. So in an ideal world, all of the accident periods would have development curves that look a bit like this. So these are losses through time. So this could be the first row, 2014, for instance, and our 10 years of development end up close to ultimate loss. And these types of well-behaved data sets can be modeled with things like growth curves, which we heard earlier. But in reality, loss development curves are highly variable, and they might not tell us great information about ultimate loss. And we don't just want to assign all this variability to some residual noise parameter. So it's useful to split up this development pattern into two states. We've got a body process, which is a flexible process, usually occurs early on in development time, and then a tail process, which is a smooth process, usually towards ultimate loss. The most common method by far in insurance modeling is the chain ladder method, which tells us that the expected value of losses for an accident period I and development period J is the previous losses multiplied by some scalar factor, alpha in this case. And alpha is the link ratio between development period J minus 1 and J. And so this is really flexible because we're just estimating this vector of multiplicative factors. But the chain ladder method is only applicable within the training data. So development periods outside of the training data that we might need to estimate to get to ultimate loss, it can't extrapolate outside that domain. And so it's common to combine the chain ladder method or some other model with a tail development model, which is usually a smooth curve parametric form curve that takes you to ultimate loss. And the intuition behind this is that you fit chain ladder to some time point here, tau, and then you fit the tail development model to some window of the training data that matches the model's assumptions. And then you predict up to tau using chain ladder, and then after that you use a tail model to take you to ultimate loss, which could be 10 or 20 years in the future. So a common tail development model is a generalized Bondi model, which is simply an exponentially decaying curve on the link ratios towards flat development 1.0. So the problem with this is that tau in rho, in this case, have to be manually selected for each new data set. And I should have said the data sets are called loss triangles. That's what you'll see in that kind of triangular structure. And so because you have to manually select them, they can be difficult to reproduce, potentially biased, but also for us at Ledger, that doesn't really scale very well because every single new data set that comes to us, we need to estimate tau in rho separately. And so the idea here is that we're interested in using hidden Markov models to jointly estimate the body and tail states. So we think that, and thanks to Marco's talk earlier, we all know what a hidden Markov model is, but we assume that there's some latent state, latent discrete parameter Z, which can either be 1 for the body or 2 for the tail, and that's categorically distributed with some category probabilities theta. And the current state is only dependent on the previous state, and that is dictated via a state transition matrix here, capital theta, where the rows of the state at the previous development time point and the columns of the state at the current time point. So pi is the probability of being in the body at j minus 1, and then you probability of transition to the body again at time point j, 1 minus pi is the probability of being in the body, transitioning to the tail, and vice versa for 1 minus nu, tail to body and tail to tail. So this is the fuller model definition. I won't go through it line by line, other than to pick out that we assume losses are log normally distributed with a mean that depends on the latent state. And all the priors in this model are standard normal on the unconstrained scale, except for the log alpha. These are the link ratios that come from the chain ladder process that receive a normal distribution centered on 0 with a standard deviation that is inversely proportional to the development lag. And the reason that we do that is because we're more likely to be in the tail state later on. And so the link ratios from chain ladder are just pulling directly from the prior. This just helps control those samples when we're making predictions so they don't get too wild.
Can I ask a question here?
Yeah.
How are there 4 parameters for the category? Why is the parameter a matrix then? Theta ij?
So we're estimating these transition probabilities. Is that okay?
Maybe the clarification is are the entries in theta ij constant? Do they vary with the indices?
Well, we do have different variants. In this case, here, these are constant across time.
Okay, good.
Yeah.
Thank you.
And so the categorical distribution is taking the row at the previous time point, and then you get your category probability, your body and tail probability. And so with the 3 model variances, one, you can transition from the body to the tail only. You can't transition from the tail back to the body. The second is a case where you can transition between all states. And then the third is one that we assume the body to tail transition probability increases with development lag. And there's obviously many more variations you could look at, but in the types of data sets that we have without too many covariates, you do risk unidentifiability if you do that. Okay, so if you've worked with hidden Markov models in the past in Stan, you know that Stan can't sample from discrete parameters, and so we're left with the task of marginalizing out the latent discrete parameter from the likelihood. But doing that in a naive way is quite inefficient. So we assume that at first, the first development lag j is equal to 1, that we start in the body process, and then we, at j is equal to 2, we have 2 possible paths for the data. Either we could be back in the body again or in the tail. At j is equal to 3, we have 4 possible paths. At j is equal to 4, we have 8 paths, and obviously this is increased exponentially with the number of time points. And so you then do some Googling and you find the Stan manual. And that takes you to something called the forward algorithm, which I won't go into great detail with, but it's a way of refactoring the likelihood statement, so it's much more efficient to marginalize out the latent state. And it does that by storing these joint probabilities of all the data up to a certain time point and being in a certain latent state. I've put more details here, including for one accident year, how you'd write out the joint probability of the data and the parameters. And again, I won't go into details here given the time, but this is, if you want to come back and look at the slides, this is a stand snippet of pseudocode that you can look at how you write it out. So first, on this model, we looked at some simulation-based calibration, which, if you aren't familiar with it, it's just a principled way of checking the implementation of a model using prior predictive simulations. And the fact that these are all mostly uniform for all these different parameters and quantities meant that we had some confidence in the implementation of the model. We then looked at some numerical examples where we simulated these lost triangle data sets from the hidden Markov model process and then fit the hidden Markov model in the two-step process and as a sanity check. So the top row here are the data points as circles and the triangles are test data points. The lines are samples from the posterior predictions. And the bottom row is the same, but for the two-step process. And in nearly all cases, the out-of-sample predictive accuracy using ELPD is higher than the two-step process. The one exception here is the second column, second accident period, where the two-step process actually beats the hidden Markov model for the one out-of-sample data point. And the reason it does that is because the manual selection of the tau and rho cutoff points for those two-step modeling process exactly matches the data generating assumptions. And so it's an important story that if you can pick those points as that completely match the data generating process, then usually that's going to help fit in the two separate models. But for all other accident periods, then that hurts the predictions, because if those accident periods have different cutoff points, then you're going to either underestimate or overestimate the losses. And we also looked across some numerical simulations whether we can recover the latent states. So here you see a histogram of the classification accuracy, and we found that we could estimate the body and tail states on the out-of-sample data accurately. There are a few cases where we have poor accuracy, and that's usually down to the structure of the data that I'm happy to speak a bit more about if needed. We then also had 200, or around 200 data sets across 4 different insurance lines of business from a paper in the literature. And these had 10 by 10 full triangles that we could then split up into the trained data set, as we would usually see, and a test data set. And then we evaluated the hidden Markov model and two-step process using ELPD, RMSE, and also looked at calibration as well. So this plot shows ELPD, and RMSE, plus or minus 2 standard errors across the different data sets. The rows are different lines of business. Don't worry too much about those at the moment. And the way to read each panel is that they're ordered by model performance, and the top model is the best performing model on average. And in nearly all cases, the hidden Markov model variance beat the two-step process. We calculated standard errors here because even though we actually have the test data in this situation, we know that this is just one possible sample from this test data because these triangles are going on and on and on through time. And so it might be that we want to be conservative with our estimates and calculate some measure of variability. The calibration plots indicated that these models are not that well calibrated. So in an ideal world, all of these will be more or less uniform, these histograms. Again, you have models in the columns, and then you have insurance lines of business in the rows. And the calibration plots indicate that our predictions are often quite uncertain, too uncertain against the test data. But this is something that has been found before. It occurs in the two-step process. It's occurred in other models in the insurance industry, literature, not even a two-step process, just single models. And this is something that we're working out, but I thought I'd include this for pure transparency. And we can also look at things like the average probability of being in the tail state by different lines of business, which is helpful for some domain-specific knowledge and validation of the model. So here you see different heat maps. These are the triangles that you saw at the start, but obviously with the lower diagonal filled in with predictions. We've got the body in the blue and tail in the red, and the intensity of the color is more likely to be in that particular state. We start in the body in each of these triangles. The top row shows private car insurance, and that shows that it transitions to the tail with quite a high degree of certainty very early on. And that is to be more expected because in private car insurance, people have accidents. They usually ring up their insurance company pretty quickly. Things on average get sorted out quickly. And then we have a speedy development curve to ultimate loss. For the second row, which is workers' compensation insurance, that's not quite the case. The transition to tail is not as certain on average. And that makes sense because in workers' compensation insurance, it's so-called longer-tailed. So it might take longer to go through claim litigation processes. Claims might only be reported much later. So you can have some shocks in the development curves later on if someone has submitted a claim or reported a claim after only becoming ill many years after working somewhere, for instance. And similar in the bottom row, this is general liability insurance, where the dynamics are similar. So you're more likely to potentially go back into the body or not as confidently be in the tail later on. So that's all I have. There's an archive preprint for this model and also some GitHub code available to reproduce all the results. And if anyone's got any questions, then I can have them. No, so yes, it's an important point. We're usually working with the aggregate loss triangle, but obviously that data is made up of many individual level claim and policy level data sets, and that's a different beast because you could have millions of potential customers, and we often don't have access to that data, particularly on the larger industry meta-analysis level. It would be great if we could, but I haven't tried that yet. Yeah.
So I was initially a bit surprised that was even allowed, and I saw from that last part, it looks like it does sometimes happen. I wondered if that is maybe some third component, which is like getting some zoom into the body.
Yeah, it could be. In this case, body and tail are really loaded terminology, but really it's a flexible process and some smooth process with more constraints. And so if you have a case like, for instance, take 2020 in car insurance, the end of the development curve, you're going to have some spike or it could be, depending on what line of business you're looking at, but you can have some bumpiness in the tail, and that might be better described by a chain ladder or something more flexible than the tail process. So that's what that really means in that situation. Thank you.